Chapter 17, Electrochemistry. So let's just review our terms. So we have an oxidation-reduction reaction, or we just refer to it as redox. In these types of reactions, we are looking at a transfer of electrons. So electrons are flowing. Oxidation is the loss of electrons or an increase in positive charge. Well, not or, and. So you lose electrons because they're negative, your charge will increase. So this means you can go from 0 to positive, or you can go from a negative to 0. Reduction is the gain of electrons and also the reduction of your charge. So your charge goes down. So you can either start neutral, which for most elements that are nonmetals, they start neutral. They gain some electrons to become negative. Or you could look at a positively charged cation that is gaining some electrons, and then the charge goes down to 0. The reducing agent is the substance that is being oxidized, and the oxidizing agent is the substance that is being reduced. So they are just the opposite. Reducing agent goes with oxidation. Oxidizing agent goes with reduction. And then we have the study of electrochemistry, which is looking at different types of redox reactions, where they are applicable, creating different types of batteries. We see this with fuel cells. We see this with electroplating. So there's a whole field of electrochemistry. So for review from chapter 7, how do we balance oxidation-reduction reactions? First of all, you take the overall reaction and split it into 2 half reactions. So this is mostly going to be helpful for you guys when you're looking at a line cell notation, because otherwise, if you're given the equation within this chapter, it has already been balanced for you. But from the line cell notation, you would have to know how to balance the equation. Also keep in mind that you can find the balanced equations, the half reactions, listed in that standard reduction potential table. So we have this overall equation here. Where did we get these coefficients? Why is there water? Why are there protons? So here is our split, our reduction reaction, our oxidation reaction. And keep in mind that when you do these, you always have to have the same number of electrons. The electrons that are being gained are the same number of electrons that are being lost. So we take our equation and we separate it. We have our oxidation reaction and our reduction reaction. Now, I just like to call this the ACE method because we always start by balancing our atoms first. So stoichiometry, we balance our equations. We always have to have a balance of atoms, charges, and electrons. So first of all, you're going to simply balance your atoms. If there's 2 irons on one side, we need 2 irons on the other. So this is where we would balance all the elements except for hydrogen and oxygen. Then you look at the side that has more oxygens. To the opposite side, you add that same number of waters. So if I have 3 oxygens on one side, to the opposite side, I add 3 waters. Because for every water molecule, there's 1 oxygen atom. Then I look at how many waters did I add, and you're going to add double the amount of protons to the opposite side. So if I've added 3 waters, I'm going to add 6 protons to the opposite side. Once I've done that, then I'm going to look at counting up my total charge, and we're going to balance those charges by using electrons. So keep in mind, when we're balancing those half reactions in terms of charges, you look at the total charge, all elements, I like to call standalone metals, any of your diatomics. Anything that is in its elemental form always has a charge of 0. Otherwise, the charge is found as a superscript on the top right-hand side of the element, or polyatomic. So we add up all the charges on the reactant side, we add up all the charges on the product side. Whichever one is bigger, we ask ourselves, what do we have to subtract from that side to get them to equal each other? Whatever number you've subtracted, that is the number of electrons that you will add to that side. So if our half reactions have 3 electrons for the oxidation, 2 electrons for the reduction, we have to have those electrons equal each other. So you're looking at what do I multiply each equation by to make this happen? Well, the lowest common multiple of 3 and 2 is 6. So I would multiply the reaction that has 3 electrons, I would multiply everything through by 2. I would then multiply the other reaction, everything through by 3, because that was the one that had 2 electrons. So 3 times 2 is 6, 2 times 3 is 6. So we're just looking at that. So once we have done that, so we balanced our atoms, we balanced our charges first just by adding in the necessary number of electrons. Then we balance our electrons by making sure that they are the same number on both the product and the reactant side, and if necessary, multiplying by some common factors. Then we add the half reactions back together and cancel out any identical species. So your electrons will always cancel out, and sometimes, depending upon what the redox reaction is, you might be able to cancel out some waters and you might be able to cancel out some protons. And keep in mind that most of these reactions are happening in an aqueous solution, and it is perfectly fine for that solution to be acidic, which is why we're allowed to have protons and water floating around. So once you have added your reactions back together, you just want to check to make sure that everything is still balanced in terms of your atoms and your charges. So here's a little flow chart that just goes through exactly what I talked about. Writing your separate half reactions, balancing those out for atoms, then balancing out for charges by adding whichever number of electrons that we need to the side that has the higher charge to it. And then looking to see that our electrons are the same, and if necessary, multiplying by some respective factors to get them to equal each other. We add the half reactions back together and cancel out things, especially electrons. So if you've done this and you find that you do not have an equal number of electrons, you have done something wrong. If you've done this and your charges do not equal each other, or your atoms do not equal each other on either side of the arrow, something is wrong and you'd have to go back and fix it. Okay, so the difference between a galvanic cell and an electrolytic cell. So galvanic cells have a spontaneous flow of electrons, which means that we're changing chemical energy into electrical energy. This chemical energy is the energy of either how the electrons are being held onto an atom or how much energy is given off when the electrons are released. So this is a spontaneous redox reaction. So we produce a current that can then be used to do work. So here's an example of a galvanic cell. We have a zinc electrode hooked up to a copper electrode. The anode is always where the oxidation takes place, and this electrode is negative because this is where we are creating the electrons. The zinc is being oxidized to zinc 2+. So 2 electrons are coming off, and then going to the positive side, which is the cathode. This is where the electrons are being gained. So the copper in solution is accepting those electrons, 2 electrons, and then becoming copper solid. So microscopically, the zinc electrode is being depleted because the solid is becoming aqueous. The cathode electrode is increasing in size because the aqueous ions are becoming solid. So in this particular cell, instead of seeing a salt bridge, what we see is just a porous disk, which works the same way. And in this instance, we have sulfate ions. So the sulfate ions will flow to this side in order to stabilize the negative charge. And the and then there's probably some sodium ions floating around as well. They're not shown, but those would go to this side of the cell to replace the copper 2+ ions that are being lost. So because we're creating zinc 2+ here, we have a buildup of positive charge. That is why we see the negative ions flowing to this side through the disk. Over here, we're losing positive ions. So they need to be replaced, which is why we would see sodium ions floating to this side. So we have to have balance. Now, this 1.10, this is the volts that is created. This is the potential that is created from this electron flow, this current. And this came from the fact that we were adding the potential from the anode plus the potential from the cathode to get the potential for the cell. Keeping in mind that we're always going to take the negative of whatever your reduction potential is for the anode. So, anode is where the oxidation occurs. It is negative. Cathode is where the reduction occurs. It is positive. Your ion flow, negative ions flow towards the anode, which is negative, so the negative to the negative. The positive ions flow towards the cathode, and just in case we want to have a tricky way to remember something, this cat, the T here, just like cation, the T here stands for positive. So positive things happening at the cathode. So we have the salt bridge or the porous disk to allow for those ions to flow in order to balance out the charge differences that are being created during this reaction. So cell potential, pulling the electrons. So really it's the cathode that's pulling the electrons from the anode to the cathode. And this is what we call the electromotive force. And this is represented by this fancy looking E. So this is the potential of the cell. Our electrical potential is measured through volts. And 1 joule of work per coulomb of charge transferred. So a volt coulomb is equal to 1 joule. We can measure this using a voltmeter or a potentiometer. So in your book, we have a table listed of your standard reduction potentials. Keep in mind there is an abbreviated table in the chapter and then a longer table in the appendix. All half reactions are given as reductions. So, and we keep in mind that at the top of the table, we have our strongest strongest oxidizing agent. At the bottom of the table, we have our strongest reducing agent in terms of looking at the products. So all half reactions, all of these potentials were measured versus a standard electrode, and that standard electrode is the hydrogen electrode, which was assigned an arbitrary value of 0. Therefore, anything else measured against it, whatever that potential was assigned for that particular process, that particular reaction. And here we have listed our standard state conditions of 1 molar concentration, 1 atmosphere for gases, 25 degrees Celsius, or 298 Kelvin. So when a half reaction is reversed, you simply reverse the sign of the potential. These are all standard reduction potentials, which means that when we need to see what the oxidation is, that is why we take the negative of it. We just write the negative for our anode and then copy down the number. When a half reaction is multiplied by an integer, it does not affect the overall potential. Those coefficients are only present because in that particular reaction, that is how many of those atoms are required to react with something else. But it does not change the overall potential. So you are never multiplying your potentials by any numbers. And a galvanic cell runs spontaneously when our cell potentials are positive. So we need a positive cell potential, and that allows us then to use that energy to do work. So how do we use line notation? This is an abbreviation to describe electrochemical cells. Your anode component is always your oxidation, which is written first. Your cathode component is your reduction, and it is always written second. We have vertical lines to represent things. A single line represents a phase boundary. A double line represents the salt bridge. If you have the same state, two things that are aqueous, we separate those with commas. The concentration of aqueous solutions should be specified if it's not standard state. So if there's something besides a 1 molar concentration solution, that needs to be shown in the line notation. If no concentration is shown, then we just assume it is 1 molar. So for example, here we have magnesium to magnesium 2+, aluminum 3+ to aluminum. So oxidation of magnesium, reduction of aluminum. This is the anode. This is the cathode, separated by our salt bridge. So we have the single line here because we have solid and aqueous. We have a single line here because we have aqueous solid. Now keep in mind, if we were going to write out an overall balanced reaction for what's going on here, we would have to multiply everything here through by 3, because 3 times 2 gives us 6 electrons. We would multiply this equation through by 2 so that we can get our 6 electrons. Then we can add these equations together to get an overall balanced equation. Now, if we have something that is a non-metal, we have to make sure that we include an inert electrode like platinum for that half reaction. So in summary, our cell potential is always positive for a galvanic cell, where we're looking at what is the potential of the cathode, and then this is our negative sign that we have for our anode. So you're adding the negative of the anode. The direction of electron flow is always from the anode to the cathode. And if given the choice, if I say pick 2 things and let's make an electrochemical cell, you're always going to write it in a manner where we get a positive potential. That is what is spontaneous, and that would be a galvanic cell. So we designate which is the anode, which is the cathode. In the galvanic cell, anode is oxidation, cathode is reduction. The nature of each electrode and the ions present in each compartment. So we want to indicate what states are present. And as I mentioned in the last slide, we use an inert electrode or conductor if none of the substances is a conducting solid. So we use those for nonmetals most often. So in a line cell notation, we are always going to write the anode first, the cathode second, and we make sure that we're separating our phase boundaries, or the phase boundaries represented by a single line. The salt bridge is represented by a double line. So cell potential, work, and free energy. So how are all of these things related? So work is never the maximum possible if any current is flowing. And this is because anytime you have electrical current, there is always heat associated with that. So energy is always being lost through heat in any real spontaneous process. So there's energy that is always wasted. So the actual amount of work that we can get is less than the maximum. So here's an equation. The maximum amount of work is going to equal the charge times the potential. Here is negative work. And here we've just flipped the signs around. So also from Gibbs free energy, this tells us what is the maximum amount of work that we can get. Now, the charge is represented by the number of moles of electrons times Faraday's constant. So if we combine these different equations, we can get to this equation, which tells us that the Gibbs free energy under standard state conditions equals the negative of our number of moles of electrons times Faraday's constant times our cell potential under standard conditions. So that means when this is positive, a positive times a positive times a positive with a negative sign in the front means that overall this is negative. And we know that when delta G is negative, this is a spontaneous process, which means whatever amount of energy then is associated with this, this is what we can use to do the work. So what happens if we change our cell potential, or what happens if we change our concentrations away from a 1 molar solution? So here we have 2 silver electrodes. We notice that under the oxidation, this electrode has been not dissolving, but the silver ions, or the silver solid, is becoming silver cation. So this is depleting, and over here this is increasing. Now we have a 1 molar solution over here. We have a 0.1 molar solution over here, which means that we have a smaller amount of concentration of our products than we do our reactants. Therefore, if your concentration of your products is less than the concentration of your reactants, we can actually create more cell potential. So at 25 degrees Celsius, the E of our cell equals the E naught of our cell minus 0.0591 divided by N times the log of Q. In your textbook, it's 0.0592. In different textbooks, it rounded things differently. Don't get hung up on that. Keep in mind, this Q is our reaction quotient, which means you would be writing out an equilibrium expression and plugging in respective concentrations to figure out what Q is. When Q is really small, the log of a really small number is negative. So then we would have something negative times something negative would become positive. So we can increase our cell potential when the ratio of our products to our reactants is really small. This means that we need to have more reactants than we do products. Hopefully this makes sense, because if you're already starting with a bunch of products, we cannot get a lot of electrons from that process. Our electrons come from our oxidation, so we need those to be in higher amount of concentration than our reduction. If we change this to K, which is the equilibrium constant for a particular reaction, then cell potential becomes 0. This is when your battery is dead. So we can no longer create an electron flow. Your cell potential then is equal to 0.0591 divided by N, your number of moles of electrons, times the log of your equilibrium constant. So cell potential becomes 0 at equilibrium. Delta G becomes 0 at equilibrium, and we can no longer do any work. Now we can recharge our batteries by plugging your battery in, or your cell phone or whatever, that's what you're doing. You plug it into the wall, you use that electric current to force the electrons back the other way. Then you unplug it and you use it, and then now we have this galvanic process of spontaneous electron flow within your battery. So this is what happens. Now, eventually, this charging and discharging of your battery, because energy is always lost as heat, eventually your battery can no longer be charged. So it's not truly a reversible process. That is why when you have your battery, you should let it charge, or you should let the battery power go down to almost 0 and then recharge it to the full potential, and do this each time in order for your battery to last the longest. And this way you're actually minimizing the overall loss of energy due to heat. So electrochemistry is very applicable to our everyday lives. On this chapter exam, I've asked you to look up some information about fuel cells and electrolysis. Please do so, cite your references, and do not copy anything word for word. We went over how to solve these equations. We talked about how we find cell potential, how we balance reactions, how we determine the number of electrons. And we also talked about the relationship between Gibbs free energy, cell potential, and the equilibrium constant, and what those values should be, what the magnitude means, what the charge, the sign means on delta G and cell potential. So good luck. It was a successful semester, I hope, for everyone, and I will see you all soon.